So good morning, everyone. My name is Brendan Bradley. I'm the QuakeCoRE director, and it's my pleasure to be able to chair this seminar and introduce our speaker, Matt Gerstenberger. I suspect many of you who are joining the call, part of the reason is because you saw it's specifically Matt speaking, and therefore you're relatively familiar with who he is and his role as leader of the National Seismic Hazard Model. But for those of you that are not, Matt's a principal scientist at GNS Science. He's been there since about the mid-2000s, 2004, Matt, I think, or on and off well before then.
Yeah.
In a full-time and ongoing capacity, coming up about 20 years. In particular, the National Seismic Hazard Model that Matt will be overviewing today was really a major science advancement for New Zealand, in that prior to commencing this project and now completing it in September last year, the last instance of the model was 2010, but that was a relatively small update. And the last significant update prior to that was in the early 2000s that informed the New Zealand building standard in 2004. So really a 20-year science update, and a huge leadership role that Matt undertook, and having both pretty much everyone in New Zealand that has something to do with seismic hazard involved, but then also a significant amount of international leaders. And something that Matt probably won't mention himself, but there's been huge recognition for the National Model Project as really leapfrogging many of the international equivalent projects that have happened in the US and Europe. So big acknowledgement of the leadership that Matt's had. Obviously the model was delivered in September, but now there's still significant work in terms of communicating what the model results mean, and also scientifically in terms of trying to understand when you make such a large science advancement, what some of the actual unintended consequences of that science might be. So there's still a long road ahead in terms of further research development. So with that, pleasure to hand over to Matt, who will give us about 25-30 minutes presentation, and then a chance for question and answers. Feel free to make some initial questions in the chat, or you'll be able to raise your hand and speak directly to Matt at the question time at the end. So Matt, hand over to you. Look forward to hearing your presentation.
Thank you very much, Brendan. Let me get everything. Looks like you can see my screen now. I was trying to, sorry, having a particular issue here. Great. Okay. Well, thank you very much, Brendan, for the chance to present this morning, and thanks everybody for coming along. What I'll be presenting today is the work of a huge number of people who all have done a pretty awesome job on this. So thanks very much to everyone who's been involved. So just overview of what I want to go through today is just a bit about the process and the review of the model and the team that's been involved. Then I'll get into what is the seismic hazard model and how do we put it together? What are some of the key results, and what are the main things that are really driving those results? And then finally, I'll just show some of the tools that we've got online, and a couple of new tools that will be coming very soon that you can use to explore the model results. So probably everybody is familiar, but the model is producing probabilistic forecasts of earthquake shaking for the next 100 years. So we're really stopping at the surface of the earth, so we don't get into impact at all. This is just about shaking. It's not about risk. And it is this 100 years. So national models in the past have nominally been time independent, and we've shown why that actually is something that's not really that feasible to do. So we've moved towards this 100-year time frame, and it also puts it much more into the context of the decisions that are being made based on the model. It is a probabilistic model, so it's based on kind of our statistical and physical understanding of earthquake shaking in the past, and there's clearly a lot of uncertainty around that. So in the end result, we have a distribution of shaking, not just a single number, and that again, that's a big change from the past. It's not just a single range. The true forecast is a distribution, and I'm trying to emphasize that to people and encourage people to, if not use that directly, to at least understand that when they're making decisions based on the model. And I guess that that uncertainty, it's really coming from when we have something as complicated or as complex as earthquake forecasting. It's just not reasonable to expect there to be a single consensus model. There is no such thing. The science isn't at the state where we can have a consensus across that. And we really have embraced that uncertainty and made it an important part of the model to bring in the wide range of, I guess, essentially possible futures based on what we understand about earthquake occurrence. And to that end, we brought in kind of 50 to 60 people from across New Zealand and around the world. So some of the best hazard models around the world. We had a pretty great team that were involved in that. So that was actually really cool to work with this team. In the review process, we used what's called a participatory peer review panel. This was our technical advisory group. So this was about 17 people, about half of those were international scientists from around the world, and about half were technical end users, largely from New Zealand. And they were involved from the very beginning at a detailed level, looking at what we were doing and critiquing and giving insight and so on. So it was a time-consuming process, but it was very beneficial, and I think it was very worthwhile to have done that. And then over the top of that, we had this assurance review, which was looking at the processes that we're using, and that was all positive in the end. So how do we make the National Seismic Hazard Model? So despite the name, it's not just a single model. It's actually a mashup of many different models. I couldn't tell you how many are in it in the end. But at the top level, there's two ways that we tend to break things down. We talk about the rupture model. So that's when earthquakes occur, where they will be in what magnitudes. And then the other part of that is, so given each one of those ruptures, what will the ground shake? And that's the ground shaking model component. So we've got those two components. And in the past, prior to 2022, each one of those components consisted of a single model, which then resulted in what is essentially what was a single estimate of ground shaking for each location. Now in 2022, we've moved far beyond that. And for each, the rupture component, we have many possible models. And for the ground shaking component, we have many possible models. And this is then what's led to this distribution of possible shaking for each location that we have that really is the true forecast from the national model. The basics of the model are pretty simple, that, like I said, the future is going to look like the past, and we use as many data sets as we can to get at that. And we have data sets spanning many different timeframes, from tens of thousands of years to a couple of decades. And each one of these data sets tell us something different about the earthquake occurrence process, and we need to include them in the model. But they also have their own limitations and their own challenges with them. So we get the best forecast by bringing them all together. And then I guess the additional part of that is kind of the regions and where the data are coming from. So we start out, we use as much New Zealand data as we can, but clearly we don't have enough. So we supplement that with global data in all aspects. But again, the global data, I mean, there's lots of large earthquakes, but there's just not enough really to be able to constrain the model well. So from that, we fill in these gaps with our kind of physical and statistical understanding of earthquake occurrence. But the upshot of all of this is that using just earthquakes from the last 1 to 200 years in New Zealand is a poor predictor of the future, and we know that well. So some key conceptual differences from past national seismic hazard models. I've talked a lot about the uncertainty. That's obviously been a big one. And this has come by looking at multiple data sets and multiple scientific hypotheses and allowing these all to go into the model. And this has then allowed us to, in the past, for large earthquakes, we really just had a few hundred ruptures, where now we're modeling thousands of potential ruptures. So we've brought this in with complex multi-fault ruptures, which on one hand may seem to be mostly important for the risk context, but they actually affect the overall energy balance of the model. So they become important for kind of smaller, higher probability ruptures as well. So that's a big change. We developed specific models for low seismicity regions, which I'll mention in a second. We've moved to this 100-year forecast instead of the nominally time independent. Ground motion models, this is a big one. This is one of the biggest changes overall to the hazard, is coming from, instead of using just a single model, we're using modern models, many of them, where we've got much more data available. And the final one is the work that we've done, and just to understand how many earthquakes will occur and what is the variability on that, that we've done quite a bit into developing those models. So on the rupture side, I'm not again going to go into details of everything. I just, 4 of the key components that really matter. I talked about the rupture complexity, and I'll go into that next. The Hikurangi, I won't talk about that today, but that's obviously a big one. And there was a lot of effort put into how we model earthquakes on the subduction zone. Lower seismicity zones, I'll talk about a little bit. And then the final one is this just overall, how many earthquakes will occur and what is the potential variability in the number of earthquakes that we could see in the next 100 years. So on the rupture complexity, I think the most basic point in the simplest way to look at it is if we looked at the Wellington Fault in previous models, there was just one rupture that was considered, say, for this particular region. There's one magnitude, no uncertainty on where it would be, and so on. And importantly, there was no connectivity with the Wellington Fault with faults around it. And we know there's no strict boundaries on faults, but that was something that was done as a modeling construct. And from the last 200 years, we know well that ruptures can be complex. They're not just these isolated events. They do interact with the faults around them. There's considerable uncertainty in the magnitude and length. And we have all of these different data sets, and each one of them gives us a slightly different view into the future and how these complex ruptures may occur. So just one example here, we're looking at this part down here is what's generally considered the Wellington Fault. And in the past, you would have had just a couple of earthquakes that were put onto here. And what I'm showing here, and they would have all been isolated to those sections. What I'm showing here is one magnitude 7.7. This is a low probability rupture in the model, but it is there nonetheless. And this is one that ruptures from Cook Strait through to Palmerston North. So then if we look at the whole, move over here and we look at the whole collection of ruptures, so you'll notice we're looking at the Wellington Fault here. So that's the same that you're seeing here. This is showing all earthquakes that this part of the fault participate in. So when they originate here or they originate somewhere else and it ruptures through. And if you look at kind of magnitude 7s and greater, you can see we have this whole distribution of magnitudes from 7 up to whatever that is, 8.1, 8.2-ish, something like that in this particular model that we're looking at. And importantly, if we look at what was done in the past, I've just drawn this on here so this isn't strictly correct, but it's kind of just a general idea of what we had. In the past, we would have had just something like these 4 earthquakes that were represented by what this section of fault participated in. They would have been necessarily smaller magnitudes, so kind of moderate magnitude 7s, but they would have had to have been higher rates because we weren't accounting for the energy that is taken up by these larger events. So by not having the larger events in there, they weren't available there for the risk understanding, but they were also effectively bringing up the hazard due to the smaller earthquakes. So there's quite a bit of knock-on consequences from that. And this is, I forgot to correct my numbers here, so I've got the rates wrong here, but this is just showing all ruptures that pass within 20 kilometers of Wellington. So you can see there's some quite big ones in here. All of these join in a rupture that goes through Wellington, but this is down to rate of 10 to the -6, so 1 in a million, so quite small ruptures here. I'll show more of that in a second. Sorry. Okay, now on to the lower seismicity zones. So as I mentioned, the lower seismicity zones in the past have kind of always come along for the ride, and there haven't been specific models developed for them. So they use the same methods that have been developed for high seismicity regions to apply to these lower seismicity regions. But what we've shown is that these regions are poorly characterized by those types of models, and the rates are not well characterized by the data that we have. And we've shown that by reducing the precision in the model, you're able to account for that. And we've done that in 2 ways. So we've done a reduced spatial precision. So we've got these big, broad, uniform zones, which are defined based on geodetic strain. And it's really just looking at the low seismicity region. So say from Hamilton north and Otago and Southland down here. So to ignore kind of the belt through the Alpine Fault and so on. So we have this reduced spatial precision. And what I mean by that is we don't distinguish spatially anywhere within those regions for this component of the model. We still have the fault model, but for this component, we don't account for that. And we also account for or reduce the precision basically in the rate component or the temporal component. And what we've shown is that when you only have a small sample of earthquakes, there is a bias in the number of events, and there is also increased variability into the future based on that. So we've accounted in the rate model, we've accounted for those 2 things. And what that means then is in these regions, we have an increased earthquake rate forecast, which then leads to increased earthquake hazard. And this is affecting those lower seismicity regions. So that everything I've been talking about so far is really talking about the rupture modeling. And then the next part is the ground shaking. So when this particular fault goes, what is the ground shaking going to be? And the first step along the way to that was to revise the New Zealand ground motion database, and there was a huge amount of work gone into that. It's actually quite a complicated and difficult thing to do. And this is just showing that the database broken down by crustal, interface, and subduction slab. And at first glance, it looks like there's a lot of data there, and there is, but you'll notice in these triangular regions, these are near source. So this is distance from source here, and magnitude. You can see it's deficient in the earthquakes that we care most about, kind of for impact. So we need to still supplement that data with international data. So we then, it's back to this point of using many models. So there's insufficient data from New Zealand, and really when it gets down to it, there's insufficient data globally. The data samples that we have are very likely biased, but we don't necessarily know what that bias is. So then there's the multiply hypothesis of basically how do you model that shaking data, and you create different models basically to represent the different hypotheses. So that gives us a distribution then of the hazard, and you can then reduce that down some by developing specific models for crustal, subduction, and slab, and so on. So each one of those models is regressed against the data, and you fit a number of parameters, and it's not necessarily strictly the way you normally do a statistical model fitting, because we do have these data deficiency problems, and we do know quite a bit about the physics, so that can be used to kind of optimize how those models are fit, and that results in this range of possible shaking highlighted by those models. And this is just an example on the right of a couple of different models plotted against the New Zealand data that's in the gray circles for one particular situation, but I think I won't talk about that one too much. So if we look at the changes from the 2022 model compared to past models, there's pretty significant differences. And a lot of that is coming from, we have the last data used in the past models was 1996. And now we've got 25 years of additional data, both in New Zealand and globally, and huge advances in our understanding. And the first important change from that is different spectral shapes. So if we look over here, we're looking at subduction interface, and this is a magnitude 8.5 at 25K. Here we have the intensity, the spectral period that you're looking at, and here's the amplitude. And this lighter blue line here is the prediction, the mean prediction from the model that's used prior to 2022, and the rest of the lines are the collection of models that are being used in the 2022 model for this subduction interface. And if you're not familiar looking at this, it might not look like it's all that difference, but when it comes down to it for hazard calculations, these are pretty significant differences that come from this. And there's also differences in magnitude and distance behavior of the models. And also importantly, the basin effects are kind of implicitly accounted for in the new model. So that's a big change from what we saw in the past. And this was looking particularly at subduction, but we see similar differences across crustal and slab as well. And here's just the subduction logic tree that we're using, and just suffice it to say that there's a lot of models in here, and it's quite complicated to account for this uncertainty. And I'll just point out that there's two models, the Peter Stafford, who many people will know, and Gail Atkinson, who adapted their international model specifically to the New Zealand data to provide what we call these New Zealand backbone models to give better fits to the New Zealand data, and they're an important part of the work that was done. So now I'll go into hazard results a little bit. And first, just some of the metrics that we talk about that maybe everybody's familiar with, but probability of exceedance is a key one, and I'll talk about that next. We've moved from using New Zealand site class to VS30, and that's been a pretty significant change. And I point that out because it actually complicates how you compare to past models, because New Zealand site class and VS30 don't translate all that directly well to each other, so you get differences based on what VS30 that you're looking at. And then finally, there's the intensity. And I just bring all of these up to say that the amount of change that is seen is really dependent on the set of metrics that are being looked at, and that can be quite variable. So I just wanted to talk about this terminology thing about return period versus probability of exceedance, and what is the correct terminology. And I just wanted to slightly encourage people to stop using return period, because technically it is not correct, and it can lead to some misunderstandings, as I've seen a number of times over the years. And I just wanted to talk about a little bit about where that comes from. So if you just think of each one of these little lollipop says an earthquake. In this case, you have an earthquake every 500 years. So in that case, it's natural to think, okay, we've got a return period of 500 years. That makes a lot of sense. But in reality, what we have is something like this, where earthquakes are a bit more clustered in time, and it's not occurring every 500 years. But even more importantly, when we're talking about hazard, we're not talking about the occurrence of an earthquake. We're talking about the occurrence of some level of shaking. So that means you need to take into account all particular earthquakes that can affect a single location. And then kind of that regularity of the system really goes away when you start to do that. And there's no such thing really as something that's particularly representative of a 500-year time period in this schematic I put together, which is pretty realistic. But where you can start to get much better information is you think about the time period that you're interested in, say 50 years, and then you look at the probability across the entire model of exceeding the particular ground motion metric that you're looking at. So for example, if you say, okay, in 50 years, there could be a 10% probability that we might see this amount of ground shaking or more. And then you can start to tune your interest based on that probability due to whatever your risk tolerance is. So 10% probability is a relatively higher risk tolerance, and a 2% is a relatively lower risk tolerance. So that's something I'm just trying to encourage people to change the terminology that's used a little bit. So now onto the results themselves. I think probably everybody knows, but on average, the shaking has increased on average of about 50% or more across the country. And I'll just show two maps here. This is looking at the 10% probability of exceedance in 50 years for PGA of 2022 versus 2010. And we're looking on the same color bar here. So you can see there's pretty significant changes across the country. And we anticipated this coming in, and we knew it would be something like this. So then if we look a little bit more detail down here, I wanted to look at the effect of VS30. So this is looking just in the Wellington CBD. This is looking at a spectral acceleration of 1 second, so about mid-rise buildings, something like that, and the number of buildings or sites that we see. And this is a ratio. So in this case, 1 means no change, 2 means a doubling. So just within the small area of the Wellington CBD, you see a range from no change in the hazard to a doubling of the hazard to even more. And this is really coming down to this translation of New Zealand site class to VS30 and the additional uncertainty that brings into the interpretation of the results. Just a bit more into uncertainty and risk tolerance. So the maps are good at showing kind of the whole country in one particular view. They don't necessarily show the uncertainty in the same way, and they don't give as much detail. So you can then dive into a particular location. So here we're looking at Wellington with a hazard curve, and this is showing the results. This shows the full uncertainty, and it shows the results across a range of probability levels. So the way this works, we have intensity here. So we have peak ground acceleration, and here is the annual probability of exceedance. And in the upper left, we have small shaking that is more likely. And the bottom right, we have large shaking that is less likely. And then the colored bars and shaded area here, that's the distribution that's coming from the model. In this particular case, we're showing the 80% confidence bounds and the means. And then you can pick any horizontal line you want to look at here. I've just shown the 10% and 2% to look at then whatever the particular risk tolerance is for the decision that's being made. So here 10% and 2%. And then the last thing on this is just to show the 2010 model. In this case, falls outside of the 80% confidence bounds of the 2022 model. If we had kind of the 95-ish or something like that, then the 2010 model would be right around there. So just showing big changes. I think there we go. I skipped a slide. Just one last thing here. Wanted to talk about where the changes are coming from, and show this with the examples in Wellington, but just the summary is in higher hazard regions, the most influential difference in the model is really coming from these ground motion model changes that I talked about earlier. And we looked at lower hazard regions, it's the rupture model that is most influential. And we know that by looking at curves like this, where the blue line, that's the 2022 model. This orange line, I think it is the 2010 rupture model with the modern ground motion models. The red line is the 2010 model, and then this line is the 2022 rupture model with the older ground motion models. And you can see that in all different metrics that we've got here, the blue and the orange are fairly close together, meaning that you're mostly getting to the 2022 model by using just the ground motion changes alone for Wellington. And then you see the flip side of this when you move to lower seismicity regions. I still want to show a couple of tools from the website, but just put my final thoughts up first. On average, as I've said, we're getting 50% more increases in hazard. The rupture model and the ground shaking model are affecting the hazard everywhere and changing it. But depending on where you are, the ground motion model matters more, or the rupture model matters more. The hit rate in Kermadec, I didn't talk about it really today, but it's obviously still a significant source of hazard for the country. It affects much of the country, but the other faults are still there. We can't forget about them now. The Wellington Fault, Alpine Fault, others are still critical to the hazard landscape of New Zealand, are as many other faults as you go across the country. And I just wanted to show quickly the website. So we've got this website here where you've got lots of access to results and reports. I think there's 30 plus technical reports that are there. So hopefully I've chosen the right option. And are you seeing the webpage now, Brendan?
Yep, we can see it. Cool.
Okay. So this is actually a test website, so you can't quite see this yet, but you'll be able to see this particular one. Everything else you can see, but this one will be out in a week or two. This is something we've put together to allow you to analyze the ruptures themselves a bit more. So what I'm showing here is the crustal faults and everything that is within 20 kilometers of Wellington that's above some certain rate. So again, this is looking at this 10 to the -6, and over here are the statistics that come out of that particular rupture set. And there's various tunable parameters in here. You can say, okay, within 10 kilometers, we'll look at that and it'll update to that. Or maybe more interesting is you can say, okay, give me everything that passes within, let's say, 30 kilometers of two different locations. So we're looking now at the difference between, if I've done this right, between Wellington and Napier, and it should give us everything. Seems to be running a bit slow. I noticed that earlier this morning. It was slower today for some reason. Hopefully it's not going to hang. There we go. We just get just a few ruptures that are in the model that pass within those distances of Wellington and Napier. So there's lots of things that can be explored there. If we go to the hazard, kind of the default thing that most people will go in to look at are the hazard curves and the specter that I just showed. So again, you've got a list of cities that you can choose from. There's quite a few of them there, or you can put in your own latitude and longitude, VS30, and what spectral period that you want to look at. And there's a few adjustable parameters here, whether or not you want to see the uncertainty, whether or not you prefer log or linear, or you can download the data that's in it. And then for that particular metric, you can then look at any probability of exceedance that you want to look at, and you've got the same adjustable parameters here. Whoops, I turned off the uncertainty there by mistake, but then we can go to the 2% probability and do that. I'm rapidly running out of time, but I'll just show a couple things quickly here. Just so the disaggregations is the next one. So this is looking at a particular site. If you want to know what earthquakes matter the most for the hazard metric at that site, and I'll just show the default one here. That's Auckland, and we're looking at VS30 to 400 meters per second, PGA 10% in 50 years. And it shows, and the first breakdown it gives you is say, okay, is it crustal subduction interface or subduction slab? And no surprise there that when we're looking at this metric for Auckland, that is mostly coming from kind of local crustal earthquakes. And you can break that down by distance here, where you can look at magnitude and distance, and you can see there's quite big interface events that are coming in at great distances, but at very that are affecting it at kind of some high uncertainty level. And then the last thing here I just show you is the hazard maps, and I'll just point out one thing, that there's an arrow over here on the left, and if you click on that, you'll get the parameters, and you can choose from all your different metrics. You can choose the uncertainty. This is just showing a single uncertainty metric. So you can choose the fractile that you want to look at. You can look at the coefficient of variation, which shows you how the uncertainty varies in space. And all of these you can download the image or download the data. And I think I'll stop there since I've gone longer than I intended to. Thank you very much.
Wonderful. Thanks very much, Matt. Obviously, a huge wealth of information, both in terms of the science that you presented and the tools that you and the National Seismic Hazard Model team have worked on to try and enable people to take that science and actually deploy it for various projects that they're working on.